Here we present an improvised laser cutting system from our laboratory. One of the key components is laser source, the resonator, which generates the laser beam. The resonator is powered and cooled by the main control unit, containing capacitor circuits for providing the energy to the flash lamps and water pump for resonator cooling. Laser beam exits the resonator and reflects from a mirror towards optical fiber cable. On the other end of the optical fiber there is the laser cutting head. You can see the ocular, with which we adjust the laser focus point, inlet pipe for introducing the cutting gas, and cutting gas nozzle. On the second control unit, we set up process parameters, namely pulse frequency, voltage which charges the capacitor circuits, and laser pulse duration. Since our system is improvised, we use simple one-axis feeding work table. Demonstrated cutting speeds will be up to 20 times slower than in the case of industrial cutting systems. In the next video clip, we will take a look how the resonator, the source of laser light, is built. First, we see the resonator tube. At the core of resonator tube, there is active medium in the form of Nd:YAG crystal rod. Active medium is surrounded by two flash lamps, which constantly illuminate the active medium. Consequently, the active medium generates new photons of the laser light. Photon beams are moving up and down the resonator tube. At the bottom part of the resonator, there is fully reflective mirror. And at the upper end, there is partially reflective mirror, in our case 92% reflective. At this place, there is light switch, which determines the laser pulse duration. Laser beam reflects from a mirror towards the optical fiber cable. To shut down the laser beam, the position of the mirror changes and reflects the laser beam towards laser beam sink. The electrical energy for flash lamps is provided by the capacitor circuits of the control unit. Prior to laser machining, we switch on the main switch of the control unit and set unit. On our machine, we can set the following parameters: frequency of the laser pulses, the voltage to which the capacitor circuits are charged, and laser pulse duration. With this switch, we turn on charging of the capacitor circuits. Throughout this video, the following process parameters will be applied: laser pulse frequency of 100 Hz, capacitor circuits charged to 500 volts, and pulse duration time of 1 millisecond. Prior to laser cutting, we open the valve for inflow of the cutting gas. In the first experiment of this video, we will drill holes in a sheet of paper by singular laser pulses. First, we connect the optical pad of the resonator with the cutting head. Then we put the sheet of paper in the vicinity of the laser focus point. In the video, few laser pulses can be seen. Single laser pulse burns a small amount of paper in the shape of a hole. The diameter of the focus point on our system is 0.6 millimeters. In the next video, we will demonstrate the effect of the laser beam on the steel metal sheet without providing the cutting gas. Known process parameters are already set. In the next step, the work table is turned on as well as laser beam. Let's take a look at the effects on our workpiece. After wiping off the soot, we see that the material is just melted through the whole thickness and then resolidified. No material removal can be noticed on the workpiece. In the last experiment of this video, we will demonstrate laser cutting. Compressed air at pressure of 5 bars will be used as cutting gas. The same process parameters as used in previous experiment will be used. We can see that the same process parameters with addition of the cutting gas cuts the steel metal sheet through its whole thickness. With industrial laser cutting systems, the cutting speed for 1 mm thick steel sheet would be in the range of 10 meters per minute.